So reviewing Snell's law, remember that in Snell's law, that n1 sine theta 1 equals n2 sine theta 2. Right, so you can remember it that way, or you can remember that sine theta 1 divided by sine theta 2 equals n2 divided by n1, so depending on how you want to do that. And so if I have, let's say we're going from the water. Okay, you guys don't like having water above where, do you? So we'll do water down here and air up top. Okay? And let's say we have Mr. Roddy snorkeling, or scuba diving at night. So we'll put the little stars in the sky, the little moon. Okay. And Mr. Roddy shines a light from here, and it goes up to the interface between air and water. Okay? And the imaginary line here is called what? The normal. And we always measure things off the normal, correct? So reflection or refraction. And the normal, so theta 1 would be right here. If you look at this, which way is the refracted ray going to leave the water and go into the air? If it was going between water and water, it would continue straight, correct? You would assume that it would go straight out. But what does it actually do if it goes from something more dense to less dense? The angle would actually increase away from the normal. So what you would get is a refracted ray that goes like this. Pardon that it's not a straight line. And so theta 2 is now all the way across to here. Does everybody see that? Okay? And if you were to calculate this, if you knew that air's n value was 1.00. It's 1.00, and there's a couple of other things, but I'm not going to worry too much. And water's is 1.33. You could calculate, if I gave you one of the other angles, what the incident or the refracted angle is, correct? That's not a scary thing. If we go to a point where I'm going to draw my normal here, where the light is shining at such an angle that the refracted ray runs parallel to the interface between the two. So again, we'll go air and water. If theta 1 causes the refracted angle, what would the refracted angle be? How many degrees is the refracted angle?
90.
90 degrees, correct? It's perpendicular to the normal. So theta 2 equals 90 degrees. That means if this is happening where it's at 90 degrees, theta 1 is called the critical angle. Okay, so your critical angle is at the point where the refracted ray runs parallel between the two interfaces of the different densities. So if air is, what's the n value for air? 1.00. Oh, wait, I'm not going to do the extra 0 because it's actually not. And then water is 1.33. Can you guys please, I'll give you a few minutes, calculate the critical angle. Go. So as we calculate this, we remember that n1 sine theta 1 equals n2 sine theta 2. We're trying to find theta 1. We have theta 2, we have n1, we have n2. So if we rearrange this to sine theta 1 equals, what's that? N2 sine theta 2 over N1, correct? Does that make sense? If I rearrange the equation, you know what's really cool? What's the sine of 90 degrees? It's 1. So if I look at this, to find critical angle, provided that you're going from more dense to less dense, it equals N2 divided by N1. Because sine theta 2 is 1. So N2 times 1 is N2. So N2 was 1.00 divided by 1.33. If I calculate that, and I find that sine theta 1 equals, what's 1 divided by 1.33? 0.7518 something rather, right? And then to find theta, I have to hit the inverse sine button, correct? And that gives you, what was it, 48.75 degrees. Does that make a bit of sense? So you can say that the water to air critical angle is 48.75 degrees. Well, Mr. Roddy, that's really useless knowledge. Well, not really. But the really cool part about this is, if theta 1 is greater than the critical angle, if it's greater than the critical angle, then the boundary becomes a mirror. That means the light will not leave that material that is more dense. And that is called total internal reflection. And if you get an accidental wrong usage of the quiz and it says total internal refraction, it should say reflection. But that's total internal reflection. So that interface becomes a mirror. But what does that mean, Mr. Reddy? Well, if I have air to water, and I have Mr. Roddy hanging out down here snorkeling again, and Mr. Roddy sends a beam of light up to here, and that angle of incidence obviously is more than 48 degrees. What's that angle approximately? Take a guess. What do you think it is? 60? Sure. So that's 60 degrees. 60 degrees is greater than 48.75, which means the ray, when it hits here, won't actually leave. What it does is it becomes a mirror, and the reflected ray is now 60 degrees because a mirror, angle of incidence equals angle of reflection. And so that light doesn't actually leave. So if you were up here looking, all you would see, if you were looking from above up here, and you were looking down at the water, you would see a speck of light, but nothing would come out. It might just be like a sparkle in the water. Okay, you would see basically a little sparkle there, but there would be no light ray coming out. So if you're trying to be very, very hush-hush so no one knows you're underwater, as long as you shine the light at a certain angle, it's not going to leave the water. It's going to stay in the water. Because that boundary between the air and the water becomes a mirror. Ask me questions. Go.